Okay, so section 1.2, mass spectroscopy. Sounds more complicated than it is. It's actually pretty simple. It has to do with the atomic masses of elements, which you've already seen, and in some cases you've already calculated before. So mass spectroscopy is just what we use to find the average mass in AMU for an element. And how do we do this? So elements, of course, can't be weighed, so they use mass spectroscopy. Basically, we've got an evacuated tube, so a tube with no air inside. You put the sample in at one end, then you heat it up to a vapor, and then an electron beam ionizes the atoms that were heated up to a vapor. So now you've got ionized gas. That gas then gets attracted because it's got a charge, gets attracted to a plate. So if it has a negative charge, this first plate would be positive, and then on the other side of the plate, it's negative. So it approaches the plate, and then at the other side, it gets repelled by it, and then it does the same thing a couple of more times, and all of that process of acceleration is going to speed up the particles down the tube. So then it sends the particles just continue down the tube, pass through a magnet, and that magnet is going to have a greater amount of deflection if the particles are smaller. So you may remember talking about isotopes. So for example, if we're talking about the element carbon, you might have carbon-12 and carbon-14. Well, carbon-14 isotopes, carbon-14 atoms, are heavier. So they're going to be less deflected because they have more inertia, because they have greater mass. Okay? So they're going to continue on more of a straight path, still bent by the magnet, but less bent than carbon-12, which will be lighter. Now, obviously, we're not talking about just two isotopes, because in this case, each blue line represents a different isotope. So this would be an element that has 1, 2, 3, 4, 5 different isotopes. Okay? And so the lightest one would be hitting at this end of the detector, and the heaviest one would be hitting at that end of the detector. And all of this is attached or hooked up to a computer that can sense how many impacts there are from different atoms, different isotopes at different parts of the detector. So it'll tell the person that reads the computer screen that, let's say, for example, 60% of the ions hit right here, and therefore we're the lightest isotope, and then 10% hit right here, and so forth. So it'll end up creating a graph that looks something like this. So this would be for something that just has two isotopes. So what this is telling us is, whatever this element is, the stuff that has a mass, and this is along the x-axis is AMU, so a mass of approximately 35 AMU makes up, it looks like about 75%, if we do a little estimation here, of all the atoms of that element, whatever that element is. And then the stuff that has a mass of 37 AMU makes up the remaining about 25%. So from that, we can calculate the average atomic mass. And again, some of you have done this before. You just haven't seen it with the graph, which is how the AP likes to present it. So what you would do is you would simply take the mass of your first isotope, and it doesn't matter where you start. So I'll start with the 35 AMU. You're going to multiply it by the abundance as a decimal. So if I'm going to call this 75%, and sometimes the graph will already be in decimal form, but in this case it's in percent form. So I'm going to take that 75% and I'm going to call it 0.75. And I'm going to do the same with each one. So 75% have a mass of 35 AMU, 25% or 0.25 have a mass of 37 AMU, and then I'm just going to add up my answers. And if I do that, I get 35.5 AMU. I would go ahead and round for sig figs because I did some estimation here from my graph, and I'm going to call this just 2 sig figs because I had 0.75 and 0.25 with 2 digits of reliability. And so if I match this to the periodic table, you can actually figure out what element this is most close to. and it's chlorine, which has a known mass of about 35.45. So not quite 36 or 35.5, but pretty close. Okay. All right. So let's try another one. So this would be a question, or similar to a question that you might see on the AP. So it says use the graph at the right to determine the atomic mass of the element, and then identify the element. So go ahead and pause and give that a shot. Okay, now your work is not going to have to exactly match mine, but here's what I did in terms of my estimations. I said that the one that has a, and I hopefully you saw this, but there is a little sliver down here at 84, so I called that 1% or 0.01. Then I said at 86 that's about 10%. Then I said at 87 is about 7%. Again, some of you guys might have said 6 or 8 or something like that, but I said 7%. And then I also estimated 82 for my percentage for the 88 AMU sample. And so multiply all these together and add them up, and I get 87.69 or 88 AMU. Most closely, actually I didn't do this ahead of time, this most closely matches, oh, this is strontium. Strontium has a real known mass of 87.62, so pretty close. All right, guys, now it's up to you. Go ahead and try some of the problems in AP Classroom that correspond to mass spectroscopy section 1.2.